Hello, everyone, and welcome to today's webinar, Scattering Microscopy, Label-Free Imaging Approaches. I'm Susie Valdez of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Teledyne Photometrics. To learn more, visit them at photometrics.com. Now, we encourage you to participate today by submitting any questions you may have during this presentation. To do so, simply type them in to the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have any trouble seeing or hearing this presentation. I'd like to welcome now our speakers. First, Professor Philipp Kukura, Professor of Chemistry in the Department of Chemistry at University of Oxford. Dr. Francesco Reina, Postdoctoral Researcher in the Institute of Applied Optics and Biophysics at University of Jena. Dr. Philip Ellen, Product Manager at Teledyne Photometrics, and Dr. Matthew Kose-Dunn, Content Manager at Teledyne Photometrics. Welcome to all of you speakers. You may now begin your presentation.
And welcome to another Teledyne Photometrics webinar. My name is Dr. Matthew Kose-Dunn and I'll be your host for this webinar all about scattering microscopy, label-free imaging approaches. Firstly, a bit about us at Teledyne Photometrics. We design and manufacture high-end cameras for demanding quantitative research in the life sciences and physical sciences. We're a market leader for scientific CMOS technology and have over 40 years of experience with the imaging industry, becoming part of the Teledyne Group in 2019. But I'm not the only speaker on this webinar. I've also invited Product Manager Dr. Phil Allen for a product update, as well as two guest speakers who are experts in the field of scattering microscopy, namely Dr. Francesco Reina from the University of Jena and Professor Philipp Kukura of the University of Oxford. I will firstly be giving an introduction to scattering microscopy and the techniques, and will then pass it over to our guest speakers for a more detailed look into this fascinating field of imaging. Scattering microscopy techniques present an alternative to fluorescent imaging, but why is this alternative necessary? The detection and tracking of single particles is highly valuable for scientific research, particularly in the study of the cell membrane or of interactions between proteins, other proteins, and surfaces. In fluorescence microscopy, these samples can be studied with the attachment of a fluorescent probe or label in order to provide contrast and localize these substances, which can then be imaged at high speed with a scientific camera in order to characterize and track these samples. These fluorescence techniques are highly popular for this format of single molecule research. However, there are limitations. Labeling can be non-specific or incomplete. The rate of emission from a label can be quite low or irregular. And these fluorescent probes can be subject to photochemical effects such as quenching, blinking, and even phototoxicity. In addition, if there are multiple samples to label, it is important to use labels that are separate enough in wavelength to not overlap, which can lead to a crowded imaging spectrum if many samples need to be imaged, which can result in bleed through and the use of time-consuming multi-channel imaging. These drawbacks could be avoided by doing away with the fluorescence label entirely, an approach known as label-free imaging. Label-free imaging is possible due to the optical process known as scattering. While not all samples can be successfully fluorescent, every substance can scatter light in some format. Using scattering would avoid the drawbacks of fluorescence and is a near instantaneous process. By imaging light scattered from the sample instead of fluorescence excitation, the drawbacks of fluorescent labeling are avoided. Imaging using these scattering techniques can be referred to as scattering microscopy. These techniques are typically label-free. This means that you avoid the pitfalls of labeling, and these techniques need to be able to detect weak signal from a particle against a very large imaging background. You need contrast in order to see the small particles you're imaging as seen from the figure. In addition, the tracking is permanent. The sample is always scattering light. You can track it for as long as you need to, essentially, which avoids the drawback of something like bleaching or quenching from fluorescence, where there's a time limit on how long you can detect your particle for. And in terms of the resolution and speed, these techniques have nanoscale spatial resolution in 3D and microscale temporal resolution, so you can capture fast, dynamic events. Vital to certain scattering microscopy techniques is the optical process known as interference. The scattered light can be in phase or out of phase with the illumination, which can lead to constructive or destructive interference, respectively. With coherent scattering, you can achieve constructive interference, which would boost the signal and the amplitude of low scattering signals from small particles, allowing for easier detection with a sensitive scientific camera. There are groups of imaging techniques that rely on this kind of interference, known as interferometric microscopy, with the most well-known being interferometric scattering, or iSCAT microscopy. In iSCAT microscopy, the sample is illuminated and scatters light. We can see here a comparison between bright field imaging and iSCAT imaging. In bright field imaging, the reference light travels through the sample and interferes with scattered light. In iSCAT, the scattered light interferes with a reference light field at a surface. So weak scattered light interferes with a stronger reference light field. This constructive interference allows for a stronger signal, which is then detected with a camera. Here we can see the flexibility of iSCAT. iSCAT can be used in both reflection and transmission approaches, as well as wide field or confocal setups. iSCAT has also successfully been used in combination with other techniques such as TIRF, or total internal reflection fluorescence microscopy. iSCAT microscopy has a very high detection sensitivity and signal-to-noise ratio, even at very high speeds. This makes it well suited for imaging protein motility in live cells, especially interactions between these proteins and the cell membrane. Here we have some examples of iSCAT microscopy being used on live samples. In the first image, A, we have gold-labeled myosin proteins moving along actin filaments. We have microtubules being driven by kinesin motors, lipid microdomains, and formation of a supported lipid bilayer. This is all captured using scattering microscopy techniques. While iSCAT can be done label-free, as we can see from image A, you can also do iSCAT with labels. The labels in this case are high scattering particles, such as gold nanoparticles. When using these techniques, it's also important to consider the image background, which is often the same wavelength as the signal and can change over time. You can also remove it using certain algorithms or by recognizing label symmetry, but the background can also be used to gather more information from your sample, such as how the sample is moving or drifting in 3D space. There are also other scattering microscopy techniques similar to iSCAT, namely darkfield microscopy and coherent bright field or COBRI microscopy. In iSCAT, the reference field corresponds to the reflected light at an interface. In COBRI, it's quite similar to iSCAT, but the transmitted light is used as the reference field, so both light fields are in the same plane. And in dark field, there's no interference at all. You simply detect the scattered light from your sample. Another exciting technique in this field is mass photometry. There are also other scattering microscopy techniques similar to iSCAT, namely dark field microscopy, and coherent bright field, or COBRI microscopy. In iSCAT, the reference field corresponds to the reflected light at an interface. In COBRI, it's quite similar to iSCAT, but the transmitted light is used as the reference field, so both light fields are in the same plane. And in dark field, there's no interference at all. You simply detect the scattered light from your sample. These different available techniques allow for flexible experimental and optical design depending on the samples you want to image and your signal level. Another exciting technique in this field is mass photometry. The light scattered from a sample can be used to measure its mass, hence why the technique is known as mass photometry. So a single molecule on a surface will scatter light proportional to its own mass, and this sample signal will then interfere with light scattered from the surface itself. So the light from the sample will interfere with the light from the surface, and the intensity of this light can be used to calculate the true molecular mass of each particle on the surface. This technique was developed by Professor Philipp Kukura at the University of Oxford, and I think we'll agree he would be the best person to further explain this technique and its applications. So without further ado, let's hear from our two imaging experts and guest speakers, Professor Philipp Kukura and Dr. Francesco Reina.
So I'm Francesco Reina. I'm a postdoctoral researcher at the Leibniz IPST in the biophysical imaging group led by Professor Christian Eggeling. And my main research focus is into single particle tracking, and in particular single particle tracking on living samples such as cell lines, model cell lines, and trying to understand how the dynamics of particles or molecules on the plasma membrane affects the physiological function of the cells itself.
My name is Philipp Kukura. I'm a professor of chemistry at the University of Oxford. I do mostly research, but also teach. And my research has completely transitioned or focuses entirely on technology that we call mass photometry, which essentially is using microscopes in slightly unusual ways, not so much focusing on taking images and analyzing these images and learning from these images or movies, but much more to use the information to provide, biophysical or bioanalytical characterization of biomolecules, essentially. If you think about light microscopy as a thing, go all the way back to 400 years ago, it's a relatively simple idea, right? You shine light on stuff, and then you have a look. I mean, that's how everything works, right? That's how we see each other, because light bounces off my head, goes to the camera, etc. And then, in the microscopy context, you essentially do the same thing that we do, except that you use optics in order to magnify your image. So you're looking at smaller and smaller features. So the concept of scattering is kind of, fundamental to the interaction of light with matter. As long as I have slightly different optical properties that are my environment, I will scatter light, right? So because I'm not out of air, you can see me. Accepting that, the real challenge is, you want to see smaller and smaller things, and the smaller they get, the weaker the interaction is going to be with the light, and therefore, it's going to become more difficult to see. And so over the last 100 years, certainly, people have been working on developing methods to try and isolate smaller and smaller signal. The idea being, if you can separate the signal from the background, the better you can do that, the smaller an object you can see. And there's various implementations of that. I mean, the kind of original one, if you like, probably was called darkfield microscopy. And it's a relatively simple idea, right? If you think about it, let's say you have your object let's say you could hold your object in free space. If you shine a laser beam on it, some of the light will get scattered. If you look at 90 degrees to the object, the only light you will see is the light that is scattered by the object. Okay. So that's dark field because the illumination field disappears. And in fact, that works so well that you can see, single atoms with your eye. If you're an atom suspended in vacuum, you shine a laser beam on it, you can look at 90 degrees, you can actually see it with your eye. So I guess what that tells you is that in principle, this concept of shining light on stuff and look at light that bounces off of it can be exceptionally sensitive. But the problem always is suppressing the background, right? And so the reason why you can see a single atom is because it's in vacuum. There's nothing else that scatters light. So the only way the light's going to hit your eye is if there's an atom that scatters it towards you. And that becomes more challenging if you're looking at the condensed phase, right? If you're looking at actually matter, because there's lots of stuff that can scatter light and produce signal. So the different forms are, the dark field that I mentioned, that's much more similar to fluorescence. So you're trying to detect a very small signal against essentially, hopefully, zero background. And then there's lots of interferometric techniques where you more or less mix the scattered light with the light that you use for illumination. And, I'm not going to talk you through the oodles of variations of this, right? Holography would be an example of it. People have done a transmission reflect, every way you can imagine. Both have their advantages and disadvantages. It really depends on what you're after. But I would say the interferometric techniques are quite different in terms of the experimental requirements to the dark field. The dark field is more like fluorescence because it's a small signal on top of zero background. Interferometric is a slightly different beast. Because you're trying to detect small changes in a large background.
So iSCAT microscopy stands for interferometric scattering microscopy. So in this technique, we illuminate a sample with a coherent light source, and the image is generated by the interference between the illumination that is reflected by the glass sample interface and all the backscattered components of the light by the sample that we're trying to observe. So of course in the sample everything that has a refractive index different than the surrounding medium will generate a scattering signal. So in a way this is not the same as doing fluorescence microscopy, of course, because we lose the specificity inherent to fluorescent microscopy. But what we gain is in terms of signal to noise ratio and the signal generation. Because we are not limited by factors such as photobleaching or blinking or other photophysics inherent to fluorescence microscopy, we can really accelerate the rate at which we collect data. And that is, for example, a great advantage in single particle tracking. The signal is proportional to the scattering cross-section. And the scattering cross-section of an object is, of course, proportional to its mass, especially in the case, for example, of proteins. There has been applications in which iSCAT microscopy has been used to measure the mass of objects inside solutions or in living or in model samples, for example, and other similar experiments. Then now there's so many applications, it's really hard to keep track of all of them. It's a very rapidly evolving field.
Mass photometry is is an implementation of iSCAT. At the end of the day, they're very similar in the sense that you shine light on the sample and you look at the light that comes back. That's also very similar to, reflection microscopy that's been around for 50 years. You shine light on the sample, you look at the light that comes back. And it's really in the details of how you illuminate and how you detect where there's small differences, right? The way I look at it is that it's really all about what you're trying to measure, right? And, A slightly more established example would be, if you think about single molecule fluorescence microscopy, it's been around for a long time, and people have known for a long time that you can look at single molecules and you can localize them at very high precision, right? But then it was the implementation of that through switching fluorescence that kind of got you to super resolution microscopy, right? So in a way, super resolution, or at least photoactivation based super resolution microscopy, is an implementation of single molecule localization. And in the same way, mass photometry is an implementation of iSCAT, and iSCAT is an implementation of reflection microscopy, spectral microscopy is an implementation of phase quantum, blah, blah, blah. I tend to think about it, what are you after, right? And iSCAT, is really very good, and has been predominantly used in the context of single particle tracking. So the idea that because you're really good at detecting small scatterers and they don't bleach and you don't really have power limitations, you can achieve very high frame rates and still maintain very high localization precisions. You can do really good tracking in 2D and 3D, and there's lots of examples how that's been used. There's some very exciting recent work where people use it to study refractive index and properties of small particles in solution. And mass photometry is really all about pushing both the sensitivity, but also in particular the precision of individual measurements. And where it becomes really useful is, if I can tell the difference between one protein and two proteins, right, or the difference between a 50 kilodalton protein and a 100 kilodalton protein, so between different masses. We don't really care so much about tracking aspect or the localization precision. It's all about making a very precise measurement on, brief events or individual biomolecules, and then use that in order to understand how, protein complexes assemble, or how proteins interact, or, kind of, this general kind of concept of what's happening a lot in nature, which is that function is fundamentally connected to proteins coming together or biomolecules coming together and falling apart.
In our research, we are of course interested in the favorable characteristic of iSCAT microscopy for single particle tracking. We have these large scattering tags attached to lipids, and they diffuse on cellular membranes or on model lipid membranes. We are able to track their position down to the millisecond and below millisecond acquisition times. And so in that way, we can really get into the finite details on the movement of these molecules on the cellular membranes. And as more applications emerge and more collaborators approach our labs, we hope to be able to make a connection between the dynamics of these molecules on the living cell membrane and their physiological function, and how the dynamics and not just the chemical properties of these molecules have a role into the physiological functions of diverse cell lines.
Take COVID, right? First step in the infection is the virus binds to the cell. And how does the virus bind to the cell? Well, there's a surface protein on the virus, which is a spike, and then there's an enzyme on the surface of the cell called ACE2, and they bind strongly, the virus binds, and then you get endocytosis and you get infection. So one of the ways to try and develop drugs is to target that interface, right? So how do you do that? Well, one way to do it is to say, well, if I have the virus, if I find something that binds more strongly to the surface protein on the virus than the cellular receptor, then the virus won't bind to the cell. And if the virus doesn't bind to the cell, I don't get sick. Job done, right? But in order to do that, what you need methods that allow you to screen these interactions, to quantify them accurately, to understand the dynamics thereof. And yes, ultimately, you have to run an assay where you check the infectivity, right? But when you start, you start with trying to find candidates that really disrupt the interaction. And that's where I really see a unique niche for mass photometry, because it's quick, it's easy, and it gives you that key information, right? Did this happen or did it not happen, right? And that's a lot of the time what you care about.
So the benefit of iSCAT microscopy is that it's really a very simple technique to implement in a lab with a certain optical know-how. So it's basically like one could see it as a wide field microscope in which coherent light is used instead of normal illumination. So it's really not that difficult to implement. Then of course there's some other aspects that make it more complicated, like for example the implementation of beam scanning or of devices to improve the signal to noise ratio or even the resolution of this technique. But it's really quite simple, and for its simplicity it really delivers a lot, because if we compare it to other techniques that rely on simple scattering, say for example darkfield microscopy, it's a trivial mathematical demonstration to show that iSCAT microscopy has an advantage in terms of signal to noise ratio, and that is, in my opinion, what makes it very, very valuable, because at the same illumination rates, at the same illumination energy, we really can get more out of our signal, and we really can get more details. The challenge, of course, is that, as I was saying, everything in the sample that has a different refractive index than the surrounding environment will generate signal. And so we lose the specificity of techniques like fluorescence microscopy, and especially TURF comes to mind, or high-low microscopy. But it really is quite simple to implement in the same setup iSCAT microscopy and fluorescence microscopy, at least in principle. There have been quite a few demonstrations here and there in literature, and so it's really a way to get the best of both worlds: high frame rate and specificity, if one can combine iSCAT microscopy and fluorescence in the same sample. So really that is the biggest challenge. That has been circumvented by using very clean looking samples, for example. When one wants to study, for example, aggregation of proteins, it's really quite easy to make a very clean solution. But then when one wants to explore the living matter, then it becomes challenging, and that's why we need to use large scattering tags, for example, like functionalized gold nanoparticles. All these challenges really are not enough sort of to dissuade us from using iSCAT microscopy, because it has shown its usefulness already, and we hope to get even more out of it in the future.
One of the issues that that we're facing is that one of the key components in these microscopes are the detectors, right? You have to actually detect your photons somehow, and you have to make images. And because in these interferometric techniques, you're always detecting your scattered light together with background light. If your scattering is very weak, that means you have to really put a lot of light on, which means you have a lot of background light. And you're trying to detect a small change on top of a huge background. What everyone else in the world is trying to do is to detect a tiny signal on top of zero background. That is almost the opposite challenge from a detector perspective. iSCAT, unfortunately, and MP, and most of these interferometric techniques, they want the opposite. So that's one challenge. Now there's many others. Turns out also light sources are not ideal. People want really good lasers. In iSCAT, you want really bad lasers, because good lasers have long coherence length, which means everything interferes with everything, but you only want a little bit of interference. So you want bad lasers, but nobody wants bad lasers apart from us. And then finally, the signals are just really incredibly small. So I mean, in a state-of-the-art mass photometry measurement requires sample drift of less than an angstrom. So you have a microscopic piece of glass, and if it moves, the size of a hydrogen atom, your measurement is ruined. Stabilization, environmental protection, all of that kind of stuff becomes incredibly important.
When we want to really accelerate our acquisition frame rate, we really need a sensor that is capable of doing that. And unfortunately, these don't come easily available. And there are many technical challenges to having a sensor that can really achieve these tens of kilohertz frame rates that have already been achieved in other techniques. But iSCAT could give us an edge because of the increased signal-to-noise ratio and the increased signal quality that we can get out of it. So of course, for single particle tracking, the dream would be to have a very fast camera, not necessarily the best in terms of quantum efficiency, or noise levels, because what we're really after is the detection. But of course, a lower noise would mean that we can really push it and really have the cleanest signal possible. Sometimes what is used is industrial cameras, so not really cameras thought for microscopy. And those have the disadvantage of having usually very high noise threshold, but reaching very fast frame rates. So usually we need to go for these cameras. And of course, as it is the case with the Kinetics, it comes to mind, we could really achieve these very fast frame rates with the very low noise levels, and that would really make all the difference in terms of image quality at the end of the day. So other characteristics that a camera for iSCAT could have are really dependent on the application that we need. For example, other applications don't really require these fast frame rates. And of course, quantum efficiency is not really an issue for iSCAT microscopy, being that we can just increase the number of photons. But sometimes you have very photosensitive samples. So you are really limited in terms of the light intensity that can be sent to the sample without risking it. And also the noise levels can be quite important. So having a low noise threshold could be quite important for application in which, for example, mass estimation is important.
In the fluorescence world, the figure of merit usually is somewhat a combination between readout speed and read noise. In our case, there's really only one figure of merit, which is the total number of photoelectrons you can detect per second. So the larger that number, the better, because that means that I can detect more light. The more light I detect, the smaller my shot noise, essentially the noise I can't avoid, and the smaller signal I can see. So the cameras that we've been using are CMOS cameras mostly, a small number of pixels, but with fast readout, and ideally relatively large pixels. Because the bigger the pixel, the more electrons you can store. The more electrons you can store, the more light you have, and so on. We want to record data at several hundred hertz, if not kilohertz. And so if you're recording data at that rate, with most cameras, you have to reduce the field of view. So you take a strip, and that goes faster. Yeah.
Really, there have been already a lot of applications that have been really quite exciting. For example, there is a sister technique of iSCAT microscopy that is gaining some traction. I think it needs to be applied more. That would be COBRI. So it's called coherent bright field imaging, as in COBRI, which is really iSCAT but operated in transmission. which operates on a similar concept for image generation. And that would be really great to apply to more live samples, especially in the fields of single particle tracking. And being iSCAT and COBRI, of course, so sensitive to small changes in mass and small changes in refractive index, I think it'd be a really powerful tool for virology. I mean, as it has already been applied for the detection of budding new viral particles from cells and the mechanism of infection, so the insertion of viral particles inside cells for infection. And I think these are really very exciting directions in which iSCAT could go in the future, because it will really give us a more comprehensive view of the dynamics of the cell. And that is really what I'm after. It is really something close to my passions. So it'll be really exciting to see it more in the future. I've seen recent applications in which dynamics of aggregation of proteins on model lipid membranes have been observed. And that is really something that really caught my interest, because if we could only manage to improve on the technique somehow on the optical side, and then we could expand the field of applications, and we could expand the kind of phenomena that we could see, not only just with iSCAT, but iSCAT in combination with other techniques, that would be really, really something fantastic for the community as a whole. I think iSCAT microscopy and single particle tracking in general are amazing applications of modern microscopy techniques. I think in general there's and this is not something that I'm contesting or I'm criticizing. There is always a large interest in imaging. There's always a higher amount of attention in structural studies, in studies of how we have snapshots of samples. So for example, fixed samples, and we can see the structure, the finite details of the structure. And this is really amazing. It's really what we've been waiting super resolution microscopy for all these decades. But there needs to be also an increasing interest in studies of dynamics, of how things interact with each other, because the living matter is always in evolution, is always moving around, and is always out of equilibrium. And we need to understand the dynamics of how things interplay with each other, because single snapshot can only tell you so much. And this is something that with the iSCAT microscopy, but also the development of new technologies for fluorescence microscopy, recent evolutions in technology, especially for fluorescence microscopy, can really make us explore another dimension of the world we live in, which would be the temporal dimension, which is so far not as explored as the three spatial dimensions.
Think about cryo-EM, right? So cryo-EM 15 years ago, not very good resolution, right? I mean, it was mostly blobs, but blobs were still good for stuff where we knew nothing. 15 years later, you can see hydrogen atoms. Right? I mean, it's amazing. And, you know, a significant contributor to that are better cameras, right? Better detecting electrons, which means that you can reduce the noise for a given electron flux. It's important to be maximally efficient at detecting your electrons. So, you know, camera technology, I think, you know, would have a substantial impact on making scattering technologies better, making them more sensitive. I think there's an uptick, if you like, of label-free technologies. You know, situations where you can detect, quantify, characterize samples without having to label them. And until recently, the general assumption always was, well, you can do that, but you're never going to be as sensitive as you are with fluorescence, because with fluorescence you can do single molecules. Well, that's really not the case anymore, right? So, you know, if you take an image of single proteins in a mass photometer, they look at least as good as images of single fluorescent molecules, which 10 years ago was unthinkable. But your ability to detect this stuff without having to use fluorescence is actually, more or less as good as it is with fluorescence. Of course, only when there's nothing else around. It's a little bit like the vacuum thing, right? So the thing that the scattering won't do is it won't detect a single protein inside a cell. Why? Because there's all this other stuff around, and how could you tell the difference? And that's where fluorescence is magnificent, right? The specificity and the background rejection, amazing. That's why I think fluorescence also makes a lot of sense in the imaging context. But the scattering is more in the detection, quantification, characterization context. And one kind of, it's always a challenge, right? You're like, oh, you've got a microscope, so you've got to make some images. And like, well, yes, but not with this, right? With this, it's much more about extracting information, about individual objects rather than imaging structure or how stuff moves around. I mean, the funny thing is, if you look at bioanalytical techniques, a very, very big proportion of them is label-free, right? Cryo-EM, label-free. A gel, label-free. SPR, label-free. BLI, label-free. Dynamic light scattering, label-free. ITC, label-free. They're all label-free. The number of fluorescence-based methods in the area of characterizing protein structure, function, regulation is actually pretty limited, right? But there always has been this, like, I can do label-free and look at the ensemble, or I can do fluorescence and look at single molecules. That's my choice. I don't have an alternative. But now you can do the label-free stuff. You can look at single molecules. So if you think about how we understand how a particular process works, or how a particular protein works, for instance, there is always this kind of structure-function relationship, right? That's been the kind of hallmark of modern molecular biology, if you like. You get the structure. Once you see the structure, you can see where everything is, and then from that you can derive the function, right? And that's been one of the major drivers of improving our understanding of protein function in the last 50 years, right? And you had X-rays, and then you had cryo-EM, and to some degree now you have AlphaFold, which is an unbelievable advance. But in many ways, I think that the next challenge, the next frontier, is to go from what are relatively static pictures to being able to understand, quantify interactions, and then ultimately transition towards dynamics.
Many thanks again to our guests, Professor Philipp Kukura and Dr. Francesco Reina. Now we've heard all about scattering microscopy techniques and applications, let's hear about the available camera solutions from Teledyne Photometrics for scattering microscopy from our product manager, Dr. Phil Allen. Over to you, Phil.
Thanks, Matt, and thanks to the presenters for their interesting work on label-free imaging. My name's Phil Allen. I'm a product manager for Teledyne Photometrics. And today I want to tell you a little bit about some of the cameras we think are ideal for scattering microscopy. As you heard from the presenters, there are lots of challenges in doing this label-free approach. There's a very weak sample signal. Often there's a very intense background with a very minor change of signal above that, which results in very low sample contrast. And if you're looking at protein-protein, nanoparticle, and membrane or membrane-membrane interactions, the binding might occur on very short timescales. So we can't integrate for a ton of time, and we have to go quickly. So some of the solutions are, we need a high sensitivity camera to get the best signal to noise possible. What that means is we need a high quantum efficiency so that we turn every photon we generate and send to the camera, and we make sure it gets turned into signal. We also need to minimize noise. We need a really high full well capacity because light in its own right is noisy. This is what we call shot noise. And if your signal is only changing by a fraction of percent, you want to lose that in the photon fluxes you'll see in low intensity measurements. So we need a high full well capacity. For these dynamic processes, we also need high frame rates. If your event is happening in milliseconds or microseconds, you might need to be imaging at hundreds of thousands of frames per second. So there are 3 cameras I want to tell you about today. One is fairly new, the last 2 years or so, and that's the Kinetics. 6.5 micron pixel, 95% QE, a speed mode with 500 frames per second, large field of view, 29 millimeters, and coming soon in 2023, frame averaging, which we'll discuss in a second. The Prime BSI Express, also 6.5 microns pixels, 95 frames per second, 19 millimeter field of view, ideal for your CMOS system, and frame summation on it, which I'll explain more in detail in the next couple minutes. And then lastly, our Prime 95B, back illuminated 11 micron pixel, which can go 80 frames a second. It comes in models from 18 to 25 millimeters. And the value here is it has a very high full well capacity, so it can take very bright signals and you can measure very low contrast things in those very bright signals. The full well capacity leads to lots of dynamic range if you were collecting signal that approaches that full well capacity. So if we look at the 95B with its 11 micron pixel or 121 square microns per pixel, the linear full well capacity that you'll get out of our camera is about 55,000 electrons. So with about a 1.5 electron read noise, the dynamic range innate in that camera is about 35,001. The Prime BSI and the Prime BSI Express are 6.5 micron pixels, so only about 41 microns pixel area, about a third of that of the Prime 95B. But they have a very large full well capacity in HDR mode of about 45,000 compared to the difference in signal area, leading to a dynamic range of about 28,000 to 1. And because of that smaller pixel, you get better spatial sampling. And then the modern CMOS these days, also with 6.5 micron pixels, have only about 15,000 electrons, and therefore get a dynamic range of about 10,000 to 1. So let's talk about the 95B. It's what we call large pixel imaging. Lots of folks are using this for a high mag, 100x functional magnification, where the 11 micron pixel does a great job of sampling the spatial resolution of high NA oil immersion objectives. It was the first back illuminated CMOS camera. It has a huge, in my mind, 55,000 linear full well capacity. So it gives you a ton of dynamic range. It's got the 95% QE of the back illuminated sensor, and with those 11 micron pixels, it's very efficient at collecting photons because of the large collection area. And then practically, it comes in 18, 22, and 25 millimeter field of view models that you can match to your optical system of your microscope. So real quick, this is just a summary. And again, at 55,000 electrons full, one can be working at very high dynamic range, very good signal to noise ratios, just with the default detection on the camera. Our Prime BSI and BSI Express provide a lot more flexibility while still maintaining a really good full well capacity. The full well capacity in HDR mode is about 45,000 for these cameras. Again, it's a 6.5 micron pixel, so it's much better at spatial sampling at 60x and at 40x high NA oil immersion objectives. It also has a high sensitivity, low noise mode called CMS, correlated multi-sampling mode, which ends up with about 0.9 to 1.1 electrons of read noise. And from a flexibility perspective, also uses USB 3.2 10 gigabits per second communication for data transport. And it's actually been used for some of these techniques, particularly iSCAT, in the past. But again, for these low contrast, interference, and direct detection images, the key point for the BSI Express is a pretty large full well capacity. However, that full well capacity of about 45,000 really may not be enough for some very low contrast imaging approaches. One thing we at Photometrics have done to engineer a couple of approaches to solve the limited full well capacity, limited dynamic range of some of the cameras that's been specified just by the hardware and the pixel size and settings. So one approach is called frame summation in our PVCam camera driver. You can implement, if you code your own software, it's something that will be, we believe, addressable using Micromanager in the first half or so of 2023. But effectively, it's going to add up frames in between the camera hardware and the arrival of a summed image on your computer desktop or your computer software. Effectively, it works with all of our cameras. So we could take, for example, a Prime 95B with 55,000 electron full well capacity and add up 10 frames in a 32-bit data type and output a resultant 16-bit image from those 10 frames, a reduced noise of the square root of the number of frames. It's not limited by the processing power that's in our cameras. It's limited by the processing power coded into our PVCam software. So effectively it increases the functional full well capacity, and in doing so increases the dynamic range. If you increase functional full well and dynamic range while maintaining low signal, even if you're having to accumulate multiple signal sources or multiple noise sources, you're going to increase the signal to noise ratio. And in general, that's going to increase by the square root of the number of frames you've summed. For example, if you've summed 16 frames into a resultant output image, you'd expect 4 times the signal to noise ratio in image output. It has negligible impact on camera speed. Effectively, you wouldn't notice a difference in frame rate using this unless you started measuring frame rates out to the 3rd or 4th decimal points. And the nice part is, because we're now limited by computer hardware, not the FPGAs in the cameras, we can actually accumulate up to 2 to the 16th 16-bit images. So instead of asking questions of, will my image have enough SNR, you just can dial in the SNR you need. And again, it's available with CAM versions 3.9 by 13.1 and higher. So just as a quick explanation of what I've been saying, so you could also take, for example, our camera with the BSI Express or the Kinetics with its low noise mode. In this particular case, we're talking about the 12-bit CMS modes, which have a saturation point of around 1,000 electrons, a full well capacity, which is not very large. But if you want to sum, so we get a functional full well capacity of 16,000, the signal to noise ratio in the output image is going to be 4 times greater than any one input image. And again, we can accumulate up to 2 to the 16th frames. And as long as you've avoided saturation, all the data is valid and good. Also, because this is PVCam, this is our driver software, you can code to easily switch between a raw output and some data output. And as the last bullet point says, functionally, processing itself has no effect on camera speed. Obviously, accumulating multiple frames of X time is going to have N times X output to output image. So we've also done this on the BSI Express in hardware. It was requested by a particular industrial customer. Prime BSI can sum up to 128 frames in camera and then output a single summed image. It's a great solution for working in the low full well capacity CMS mode, which each frame would saturate at about 1,100 or 1,200 electrons. And it basically leads to an increase in full well capacity and signal to noise ratio in the same way we've talked about for summing on the host computer with PVCam. We're also intending to do this for another customer, but we'll make it available to all on the Kinetics. And this will actually be not frame summation, but frame averaging. And in this case, we will be doing in-camera accumulation in 32-bit mode. So we could accumulate very bright signals in 16-bit mode and then average many frames and give a very high intensity, very functional low noise output image. Because we run the Kinetics so quickly compared to our competition on other platforms, the functional full well capacity of the Kinetics is much lower than the other prime cameras. But we trade that off again for speeds up to just under 500 frames per second in the camera. So with the Kinetics, you can either use frame summation and or starting in the middle or so of 2023, you could use in-camera frame averaging. As we've mentioned before, you're going to increase SNR, reduce noise, be able to detect very low contrast changes that otherwise would be lost in the noise. And again, we'll have more details to share on this once the feature is fully implemented in the coming year. So just as a quick reminder, the Kinetics, in my mind, is one of the most flexible cameras out there for science. It has 16-bit dynamic range mode, 83 frames a second. And as a reminder, that's 83 frames at 10 megapixels each, stretching out 3200 by 3200, 6.5 micron pixels. But it only has a full well capacity of 15,000 versus our BSI and BSI Express, which at the same pixel size have a functional full well capacity of around 45,000. It has the sensitivity mode, 88 frames a second. It has speed mode, just shy of 500 frames a second. And it has very low read noise subelectron mode. So just as a reminder for those of you who aren't aware about the general features of the Kinetics, if you wanted to take a standard CMOS camera and would go 100 frames a second and ask it to go 500 frames a second, you'd have to region down to about 1/5 of the area or about 400 rows. Use the Kinetics, you can get the full frame at 500 frames a second. That's effectively an 11 times larger area. If you were looking for field of view, the sensor is the biggest one available in the scientific market. So it's 2.4 times larger than typical CMOS, 6.5 times larger than the EMCCD. Those are area numbers. And even at 16-bit HDR kind of data, you've got much faster throughput and coverage than any other camera out there. So you capture everything your microscope can put out. And as an illustration of this, if this was a typical EMCCD or CCD image, for those of you who predate CMOS, here's a standard CMOS. Here's our Kinetics 22 in green, and then the full field of view you can capture with the Kinetics shown in the background. So quick summary, 0.7 electron read noise, 95% QE, lots of pixels to make 10 megapixel frames, 6.5 micron pixels, which work well for the microscopy world with high magnification, high NA objectives. Incredible throughput in terms of speed and data, biggest sensor area. We also, for those of you who don't have optical systems that can cover that much, have our Kinetics 22, has the same frame times as the Kinetics, same specs, but is region down to 2400 by 2400 pixels. So it matches the maximum area that a C-mount can output. So with that, I'm going to hand it back to Matt. Thank you for your time.
Thanks to Phil for taking us through the Prime and Kinetics CMOS families, as well as our frame summation and averaging capabilities. We also have a customer story from Professor Christian Eggeling, who is using the Prime BSI Express for a combination of iSCAT and turf microscopy in order to observe molecule diffusion on live cell membranes. This group required a flexible camera that could integrate into their specialized software and have made great use of the Prime BSI Express sCMOS. The Prime BSI Express is fast and sensitive and has been an ideal solution for this application, able to capture the entire relevant field of view or to create a small region of interest in order to operate at extreme high speeds. the camera was integrated into the required ImSwitch software using our provided Python wrapper and our great compatibility with third-party imaging software. And as mentioned, the Prime BSI Express gave us flexibility for both TURF and iSCAT at a high speed and across a large area without difficulty. Here we can see an image from this experiment using iSCAT with an insert as well, showing the high sample contrast against a large imaging background, picked out easily thanks to the sensitivity and large full well of the Prime BSI Express. In summary, scattering microscopy approaches provide a label-free alternative to fluorescence microscopy, with nanoscale 3D spatial resolution and microscale temporal resolution. These techniques require cameras that can detect a weak signal against a large imaging background, needing both high sensitivity, high speed, and a large full well capacity. The range of modern CMOS cameras at Teledyne Photometrics are a great fit, such as the Kinetics and Prime families. But all of our cameras have frame summation capabilities through our PVCam driver in order to increase both the full well and your imaging signal to noise ratio. That's everything from our webinar today. Many thanks for your attention. If you'd like to find out more, please contact us via our website at www.photometrics.com. And I hope you have a great rest of your day. Thanks again for listening.
And thank you for that informative presentation. We will now start the live Q&A portion of this webinar with Dr. Matthew Kose-Dunn. If you have any questions you'd like to ask, please do so now. Just click on that Ask a Question box located on the far left of your screen, and we'll answer as many questions as we have time for. So let's get started. Dr. Kose-Dunn, looks like we already have some great questions coming in from our audience. Our first question, it seems you still need to use a label that is strong scatter and track the proteins of interest. Is that correct?
Yeah, so while the scattering techniques themselves are inherently label free, as in you don't need a label to get the contrast necessary to receive a signal and do the imaging, it does mean that you can also get particles that scatter very strongly and use them as labels if you wish to do so. This would have some downsides with regards to localization and making sure you wash them off after labeling, the kind of things you'd encounter with fluorescence labels. But while these images and techniques can be label free, there's the option to use highly scattering particles as labels if necessary, depending on your application.
Thank you so much. Now, at current state of art, what camera would the presenters recommend if building in iSCAT microscope from scratch? Kinetics or something cheaper like a machine vision camera?
So in the webinar, we outlined the Kinetics and the two prime cameras, the 95B and the BSI Express. These are great for scattering because what you want is you want a full well, basically. And you can get a lot of cameras that can operate at a high speed or have a low read noise. And we offer these cameras too. But the unique capability that often isn't focused on in other applications, but is here, is the full well. And our cameras have a larger full well than similar solutions. And if the full well isn't large enough, you can still increase that further with the frame summing capabilities in the PVCam driver or in the camera's FPGA themselves. So the Kinetics will offer frame summing and averaging. The BSI Express also offers summing. So we have a range of flexible solutions for iSCAT, mainly because of the much larger full well, so you can image the incredibly, get as much of signal as you can from your sample as well as the background that it's within.
Thank you so much. And I want to thank our audience for these great questions coming in. Our next audience member actually put his name, Phil Yoon from Synchrolux. He says, as I see the readout noise is quite low, what is the signal to noise ratio from the CMOS cameras?
Yes, so the readout noise is very low. We drive this as low as possible. It's in the 1 electron to sub-electron levels for the majority of our cameras. And so this means that when you have a high signal collection and a low noise level, you get a great signal to noise ratio. It does depend on the signal that you're receiving. So the signal to noise ratio largely depends on what signal you're getting in the first place. If you're operating in a very low light area, then read noise is all the more important. You'll be read noise limited. But in general, even if you're operating with a handful of photons, the cameras have a significant signal to noise ratio. So we don't have a stated value for any of these because it depends on your application and it's quite subjective. But I've yet to see any applications where, you're getting flooded out by noise, basically.
And Dr. Kose-Dunn, does the camera operate at room temperature? What is the operating temperature?
So these cameras are all equipped with forced air cooling. So we aim for a temperature around -15 to -25. This means that you can bypass any effects of dark current. Not that dark current is very significant in this application because you're not typically imaging or exposing for a very long time. So the camera will operate at room temperature. It'll operate at any temperatures, in even very hot rooms up to 30 and 40 degrees, if we're talking about the temperature of the environment you're operating it in. But the camera itself will be aiming for sub-zero temperatures because of the cooling.
Thank you so much. Our next question, what is the relationship between mass and optical polarizability of a particle or protein? And this is a two-part question. The scattering cross-section should be proportional to the polarizability, which is dominated by the mobility of the outer shell electrons, not so much on the total number of electrons or the mass of the particles.
So I would definitely have to consult someone like Philipp Kukura again for this because I'm not an expert when it comes to the scattering aspect of scattering microscopy. But in general, my understanding is that the mass is proportional to the scattering. As for the polarizability, I'm not entirely sure. My basic go-to here is the fact that you can detect these extremely small particles even down to the atomic level while they're in a very large imaging background. So I'm assuming the polarizability of your sample may affect the scattering, but we've been able to see things that are less able to scatter light, and therefore if your sample is able to tune its polarizability, you'll still be able to see quite a lot of it, and hopefully you'll be able to get some contrast.
Thank you so much. And again, I want to thank our audience. These are great questions. We have time for a couple more. The next question, I understand the benefit of frame summation for increasing full well capacity, but I'm curious whether it would have any benefit for low light samples. Under conditions where pixels are not saturated, is there any benefit to, let's say, summing 10x 10 ms exposures compared to taking a single 100 ms exposure? My intuition is that summation would be worse under such conditions because read noise would be additive, but curious to hear your thoughts. What do you think?
Yeah, so great question. As it stands, the application of frame summing in this iteration is mainly for the additional full well capacity. If you're in a low light regime, that's another application that our cameras are designed towards. And we have cameras like the Kinetics that can go extremely fast. In order to go fast, you need very short exposure times, often in the millisecond or sub-millisecond level. So you need the camera's ability to detect sufficient sample with a very short exposure time. So you're correct that summing 10 millisecond exposures would probably not be as good as taking a single 100 millisecond exposure because the read noise will add up to a rate below the signal, but the camera will be capable of taking images at around 10 milliseconds or below regardless. And then if you're struggling to achieve the right signal to noise ratio at a really short exposure, your options are going to be to increase the light level or to try and change your fluorophore. In this regard, frame summation is mainly here to bulk out the full wall capacity and make sure you can capture your very small signal in a large background. So for fluorescence imaging, it's got different applications.
Dr. Kose-Dunn, we have time for one more question. Can label-free scattering used for 3D imaging? And if yes, how can it provide view of different angles?
Great question. Yes, to my understanding, label-free imaging can be used for 3D. This is due to the interactions of the particle with the background. Quite a lot of these applications see the background as a nuisance and want to just see the sample and not any of the background, and can smooth this out with algorithms. But the background itself does give information as to where the particle is likely to be moving in 3D space by how it's interacting with the background. So I don't know how you can provide a view of different angles. This would be more something like light field microscopy, where you can see your sample in all the different angles and you can get the direction and velocity. With scattering microscopy, I do know you have the capability to see it in 3D, but I'm not sure if you're able to view it from different angles, just an appreciation of where it is in the Z plane, for example.
Well, I want to thank you, and I want to thank all the presenters today for their presentation. And Dr. Kose-Dunn, would you like to provide any final comments for our audience before we go?
Yeah, I'd like to thank the speakers again, Dr. Philipp Kukura and Dr. Francesco Reina. At Photometrics, we focus a lot on fluorescence, low light microscopy, but it's great to also see these additional applications in other fields like scattering microscopy as well. And if I haven't been able to answer any of your questions, or if you have extra things you want to know about either the products or the application itself, we have lots of information on our website, which is www.photometrics.com. So there we have information on our products, but also applications like scattering microscopy and iSCAT as well. So feel free to come along. And if I haven't answered your questions, please feel free to email me as well.
Well, I want to thank you again for your time today and for your important research. And I'd also like to thank LabRoots and our sponsor, Teledyne Photometrics, for underwriting today's educational webcast. And before we go, I want to thank the audience for joining us today and for their interesting questions we did not have time for today, and those submitted during the on-demand period will be addressed by our speaker via the contact information you provided at the time of registration. And this webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care, everyone. Bye-bye.
Thanks very much.